Circle C0 has radius 1, and the point A0 is a point on the circle. Circle C1 has radius r is less than 1, and is internally tangent to C0 at point A0. Point A1 lies on circle C1, so that A1 is located 90 degrees counterclockwise from A0 on C1. Circle C2 has radius r squared, and is internally tangent to C1 at point A1. In this way, we construct a sequence of circles C1, C2, C3, and so on, and a sequence of points on the circles A1, A2, A3, and so on, where circle Cn has radius r to the n, and is internally tangent to circle Cn-1 at point An-1, and point An lies on Cn 90 degrees counterclockwise from point An-1, as shown in the figure below. There's one point B inside all of these circles. When r equals 11 over 60, the distance from the center of C0 to B is m over n, where m and n are relatively prime positive integers. What is m plus n? Okay, that's a lot of words. So basically we have circle C0, which has radius 1, and the point A0 is a point on the circle. Then we construct circle C1 that's internally tangent to C0 at point A0. It has radius r, which is less than 1. And then internally tangent to C1 at point A1, which is located 90 degrees off from A0, we construct circle C2, which has radius r squared. And we keep doing this 90 degrees counterclockwise spiral stuff infinitely until we approach a single point B that's inside all of these circles. That's somewhere here. And we need to find the distance from the center of C0 to that point B, where the spiral ends. The center of C0 is here, and we need to find the distance from that center to B. The center, we'll call that C. And we need to find CB. So what can we do here? Well, we notice that this is an infinite spiral. Each new circle has radius r times the radius of the previous circle. It's very predictable. The tangency point is always 90 degrees counterclockwise from the previous one, and the radius is always r times the previous one. So maybe we can map this figure onto itself using some kind of geometric transformation. Let's see if we can do that. Consider the entire figure. Let's see if we can map it onto itself by using some type of transformation. I know that's not the best circle, but whatever. We can apply a homothency centered at C with scale factor r, and we'll get this sequence of circles here. Something like that. I don't care. Yeah, just that. And then we can move it some distance to the right, such that this figure is internally tangent to the largest circle, which is C0. So we can move this red stuff to the right, 1 minus r units, and that figure will end up looking something like this. Let me just get rid of all this so that it's easier to see. That figure will end up looking something like this. And now all we have to do to get the original figure back, minus circle C0, is just apply a 90 degrees counterclockwise rotation. That will send this circle here, here, and that stuff. And we will end at the same point B. So all we need to do to get the original figure back onto itself, minus circle C0, was to apply a scale factor of ratio r centered at C, move it to the right 1 minus r units, and I know it's 1 minus r because it's the radius of circle C0 minus the radius of circle C1, which is 1 minus r. So yeah, all we did was just dilate it at C with ratio r, move the figure to the right 1 minus r, and then applied a 90 degrees counterclockwise rotation. So if we apply that to segment CB, we should get segment C1b, because B is the end of both series. The series that starts with circle C0 and the one that starts with circle C1. They both end at point B. So line segment CB, which I drew originally, if we apply exactly these steps to that line segment, we should get the line segment C1b. So let's apply them in that order. First, I said we're going to dilate at C with ratio R, so that's this segment but shorter. Then I said we're going to move it to the right by 1 minus R units. So it would look like that now. And then rotate it 90 degrees counterclockwise, so it's now this. And that's segment C1b, where C1 is the center of circle C1, obviously. So these two lines were parallel, and this one forms a 90-degree angle, so the two lines are perpendicular, and it forms a right triangle. But what else? Well, all we did was dilate with ratio R, move it right, which didn't change the length, and then rotate it, which didn't change the length either. So that's still R times the length of the original segment. And if the length of the original segment was D, then the new length would be R times D. And D is what we want to find. So we have a right triangle whose legs have lengths D and RD, and its hypotenuse has length 1 minus R. So we can form the equation that D squared plus R times D squared is equal to 1 minus R squared. So D squared times 1 plus D squared times R squared is 1 minus R squared. Now square root both sides. We have the D times the square root of 1 plus R squared is equal to 1 minus R. Therefore, D is equal to 1 minus R over the square root of 1 plus R squared. Now just plug in R equals 11 over 60 and we're done. This is just 1 minus 11 over 60, that's 49 over 60, divided by the square root of 1 plus 11 over 60 squared. That's 3721 over 3600, whose square root is 61 over 60. 49 over 60 over 61 over 60. Cancel the 1 over 60s. 49 over 61. That's the answer. M plus N is equal to 110. Thank you for watching this YouTube video. Please follow my channel if you would like to see more videos.